Right, well, hello, I'm David. I'm the coordinator of the Maths Learning Centre. This is a revision seminar for Applications of Quantitative Methods in Finance, and it's Semester 2, 2022. And I've had some requests, and the requests are about calculus so far, and they're about inflection/critical points, local maximums and minimums, those sorts of things, and also about differential equations. So now let's do critical points and related ideas. That's my heading for what you've said. Okay. So, right. So the idea, this is all about derivatives and about finding maximums and minimums. And the traditional way of representing a function is to have an x or a t or whatever it is here, and then the function's output on the y-axis, and then drawing a graph like that. And at any point, the derivative is a function which tells you how strongly sloped this curve is at that point. So if you're here at this particular point x, and this height here is f of x, then when I zoom in with a magnifying glass on this section just here, it will look through the magnifying glass almost straight, and that slope is the derivative. And so this function has different slopes at different places, so the derivative will be a formula that says what the slope is at the different places. If you put a number in for x, you'll get a formula for what the derivative is. And so that derivative is f dashed of x. That's how it's traditionally written. Or it's df on dx. That's the other way of writing it. So I could say f of x is the function, and f dashed of x is the derivative, technically the function value, and this is the at input x, and this is the derivative at input x. But I could also write y equals some formula involving x, and then I could write dy on dx equals whatever it is. Something different to that usually. And these are both trying to say the same information. This is using function notation where I had a name for the function and then the f dashed is the next function. Whereas this is talking about this dy on dx is a very small change in x and a very small change in y, and the slope is that divided by that. That's the idea behind it. Okay, so the big idea is that at a place like this, if I zoom in with my magnifying glass, it'll look like that. And here, dy on dx is going to be 0. And it'll happen here as well, and it'll happen here as well. In all of those places, the function will look like it's flat if you're very close to it, like horizontal. And so those are places where the function turns, and they're called critical points. Cool. I'm just going to check something in these notes. Yep. So some functions, though, are like this. like that, and they have sharp kinks in them, and no matter how close to this I am, that kink will always be there. And this is a place where the derivative doesn't exist, because no matter how close I am, the slope on one side is different to the slope on the other side. And it doesn't even have to be a turning point. It could be a place like this. Like that. And when I zoom in on this, it still has a kink in it. So these are places where the derivative does not exist. There is no derivative at these places. And that's because it doesn't flatten out when I get close to look like it's a straight line, and it never does, and so I can't do the slope of this line. And if I just look at half of it, it's nice and flat there, and it could have one slope, and the other half would have another slope, but they're not the same number, and so I can't figure out a single number to be the slope at this point. But notice that this maximum here happens when the derivative is 0, and this maximum here happens when the derivative doesn't exist. And so if I'm interested in finding where the maximums and minimums are, I have to find all the places where the derivative either is 0 or doesn't exist. And that's what a critical point is. So when we say a point x, we really mean a point on the x-axis. So if you want to find the critical points, you have to find all of the values of x where the function, where the derivative doesn't exist, and all of the places where it does exist, but the answer is 0. And that's what a critical point is. And it's called critical because it's important to our decision-making process. That's what critical means in English. And so, yeah, that's a critical point. There's not many examples in these lecture notes. That distresses me. Like not filled in. They're just not many to begin with, whether they're filled in or not. Give me a second. Oh. No. Oh, crap. Give me a moment. I just want to figure something out. Okay. Let's find the critical points. So the critical points are places where the derivative doesn't exist or where the derivative is 0. This function is a polynomial. It doesn't have any places where the derivative doesn't exist, so I don't have to worry about that. And the derivative will be, the 2 will still be there, and I'll multiply by the 3 and the exponent will go down by 1. And then the 8 will go away. So I've got 6x squared minus 42x plus 72. And so I need to find the places where this derivative is 0, and they'll be the critical points. What's that? I have that. And so I need to do this. And so whatever method you have for solving quadratic equations, you need to use that. So I notice that there's a 6 here, and actually 6 goes into all of these numbers, so I'm going to divide by 6. And now, if I'm lucky, I can factorize it, but if I'm unlucky, I'll use the quadratic formula. So if I can think of 2 numbers that add to give -7 and multiply to give 12, that'll be good. 7 and 0, no. 6 and 1, no. 4 and 3, yes. And so x is equal to 4 and x is equal to 3. They are my 2 critical points. These are points where the derivative is 0. Yes, you can always use the quadratic formula if you want. I would spend just a couple of moments seeing if you can think of the right things, but if it takes more than a few seconds, use the quadratic formula. So if you looked at this and you went, no, I don't think of anything, just use the quadratic formula. So you could do this, or you could have done this bit. You could have said x equals minus, so that's a and b and c. X is minus b plus or minus b squared minus 4 times a times c over 2a. 7 plus or minus, well, 49 minus 48 is 1. Oh, that's convenient. And so I get 7 plus 1, which is 8 on 2, or 7 minus 1, which is 6 on 2, which is 4 or 3. So you could have done the quadratic formula and it would have worked fine. Gives you the same answer. X is 3 or 4 other critical points. So in this course, critical points are just values of x. In some courses, critical points are the point actually drawn on the curve itself, and so you have to figure out their y-coordinate as well. But in this course, just this. Okay, so they are the critical points. They are the places where the derivative is 0, and that's lovely. Good-o. There's more to this, and I'll come back to that in a second. But I just want to do another example. I just have a question. Is it common for people in this course in Mobius's or assignments to define functions with a branch with 2 different things? Have they done that before? Like where f...